There you see a very nice diagram of the OSI model. And it's more than just a basic model. It has the names of the layers. You see those on the left-hand side of the diagram, the 7 layers. On the far right, you'll see kind of a description of what those layers do. Because if I say session, what does that mean, right? If I say, data link, what's that mean? Well, it means physical addressing, like the MAC, right? The MAC is on the network interface card. That is a physical address. It's not a virtual address, right? It's a physical address. IP addresses change, right? They're dynamically assigned typically on networks. That means that they're not physical, they're dynamic. And in the middle of this diagram is some really good stuff. These are all your favorite protocols. I will do my best to relate these to things that you do, software that you use, commands that you run, right? When you're running networking commands in the terminal, you are doing things in these layers. We did some of them last week in class. Right. And since I also said many times, and I'll say it again, we're having a quiz in week 9. I actually have the quiz right here. Let's see, here's the quiz. I'm pretty much just going to go over the quiz. And those lucky enough to have seen this video will do really well. Actually, I'm only going to go over half of it, and then I'll go over like the other half next week. So you'll have more reason to come to office hours like you should. Okay. Quick review of the layers themselves. Bottom of the stack is the physical layer. What's that mean? Wires, cables, Ethernet cables. That's what RJ45 is. DSL is a type of telephone cable. RS-232, now that's interesting. That is an old style serial protocol cable. But in the 80s and the 90s, probably the 70s, maybe the 60s even, you could connect computers together and communicate data over an RS-232 cable. I have a kit that does just that. I wonder what's in it. Ooh, this one's even faster. This has USB and parallel transfer cables for data communication. I'm going to see if I can really show that really well. That won't work really well. Let me see. Let's try this one. Oh wow, it's showing it all backwards. Oh, isn't that silliness? Anyway, you'd think it would mirror things like that. So what do these cables look like? You haven't seen a lot of these cables because, people don't use them today much. Now, of course, you have seen a USB cable. However, this one has something sneaky in the middle. What could that be? I believe it flips the data connections. So that this isn't your normal cable. That this flips the send and receive at each end. So when I'm sending data down this cable from this end, when it gets to this end, the wires are flipped around. There's 4 wires for this type of USB. When they get flipped around so that the send goes to the receive. And when this one is sending, the wires again are flipped around in that junction box here in the middle so that it's receiving. What are you cats doing? That's Sancho. Hi, Sancho. How are you going to get down now? Yeah, you don't know, do you? I might have to help him down. So this is a sneaky cable. It's not your usual cable, not by a long shot. Now this is definitely something you will not have experienced. This is a parallel cable. Now the old RS-232 serial cables are smaller. They only have 9 pins. This has 25. So what do you do with that? Well, you send data in parallel. What's that mean? It means you send data faster. Okay, hey everybody. All right, Sancho. Sancho's got his new Christmas ribbon bow on. Where can I see it? There it is. There you go, buddy. So a parallel cable sends the data in parallel, so you can send more data at a time. So it's going to be faster than a 9-pin serial cable. So I guess RS-232 must cover both. I think it does. I think it covers both data, serial and parallel communications. So anyway, this old thing is for moving data between computers, like if you're setting up a new computer. It would be very slow by today's standards. That's because it was made for like probably Windows 95, maybe Windows. I'd still work on XP. Let's see, system requirements. Oh, it needs a Pentium. That's awesome. Microsoft Internet Explorer 4.0. 95, 98, Millennium 2000 or XP. Okay. So this works with computers that span like 15 years easily of computing history. The parallel is pretty slow. 500 megabytes will take 90 minutes. USB will take 12, and on a network it would take 6. So the parallel cable is 15 times slower than a 100 base T network, which is like a 100 megabit per second network. Anyway, that's how people used to move data around. IntelliMover. Set up your new computer. You're very lucky today that the computers set themselves up through the cloud and cloud backups and re-download apps for you and things like that. All right. Back to the diagram. 802.11, that family of protocols is for wireless communications. As I said last week, Wi-Fi is part of the physical layer, any of the RF communications, cellular. Now to the data link. Physical addressing. MAC addresses attached to NIC cards on a LAN or a VLAN dictate how data is sent. So you plug your cables into a switch, which is a layer 2 device, and the traffic coming in that switch, it knows the MAC address for each port on the switch, the MAC address of the computer connected to the port, that is. So when the traffic comes in on the internet, inside the switch, it knows how to route the traffic to the appropriate port to send the data out to that computer. Now they list quite a few other technologies here. Some of them are in use, some not so much. I don't think token ring is used. Hasn't been for a long time. Probably not frame relay, but ATM might still be used as a very efficient protocol. Not a lot of overhead, designed for high quality networks. I think fiber channels in use. I don't know what HTTP is, honestly. It might be old. What else can I say about these? I'll just mention that a switch has something called some of them have a port replicator on them, so you can copy data that's going through the network on the switch out the port replicator, so you can use it to monitor what's going on people's computers. Name a device in a desktop PC that operates primarily at the data link layer. Well, that's going to be the network interface card, right? Which has the MAC address. So that's kind of cool. Now we're going to go to the next layer, the network layer. This is where you start connecting your little autonomous networks together into one big network, connecting them over the internet to each other. To do that, you have to be able to route data from one place to another. So this is where the routers live. Here, they didn't use the word router, which is kind of silly. It says path determination. Oh, the path is the route. So when you run trace route, right, you see the path from point A to point B as determined by the routers that you're going through. Uses logical addressing. Logical addressing is where you start getting your IP address. Okay? Since you don't get the same IP address on a network all the time, that's considered logical addressing. Now, you can, if doing a static reservation of IP addresses based upon your MAC address being registered for a particular IP address, useful for printers, right, and servers and things, then you can do it. It seems like, oh wait, I have an address, it's the same address all the time. Doesn't make it physical. It's still a logical address. Now what else is here? IP, we said ARP, Address Resolution Protocol. So some of you know that is a command you can run from the terminal. And it will, oh gosh, you can just show what it does. Do cool things because we have a computer. Okay, I will show you the output of ARP. Some of you know this, some of you did it in your homework, which is cool. What do we have here? I ran ARP-A. So first I ran ARP to get the instructions for you. Displays and modifies the IP to physical address translation tables used by the address resolution protocol. So we save the data. We save data about which MAC address is associated to which IP address in the ARP cache. I believe we can flush that cache too. I bet there's a command for that. Pretty sure there's an ARP cache. I'd feel really stupid if there wasn't one. So here I ran it. Now this is interesting. Add a static entry to the table. So for an IP address associated to it is 6 bytes. This is a MAC address. Now on my network, there's a bunch of devices. You can see them here. Some of these have dynamic IP addresses. Some of them have static IP addresses. The static bit, I think that's my gateway. That's my router, the .1. Why it says dynamic, that makes no sense. These ones in the middle here, 102, 164, etc. Those are basically like computers on my network, my phone, things like that. These are broadcast addresses. We haven't talked about that. Not all traffic goes one-to-one. Some traffic comes out of the network and goes to every device. It gets broadcast. And then, the receiving device does something with that information. It may need that information for some reason. Let me check something. Yes, there is an ARP cache. I didn't see a command for flushing it, but there should be. Oh wait, how do you clear it? How do you delete the ARP cache? And the answer is, oh, you use a completely different command. Okay, you can delete specific entries with the -D command. ARP-D and then an internet address. Oh, I missed that. There it is. Delete the host specified by the address. So there's an old type of spoofing where you could basically take somebody's MAC address and associate it to your IP address, so any traffic coming in would go to you instead of to them. ARP spoofing, ARP poisoning was another name for it. So when the device first needs to send data to an IP address, it sends out a broadcast ARP request. So you could see this in Wireshark. You could open up a Wireshark window and it will be like, who has, and it will be an IP address. And the response, if you are that IP address, it'll come back with the MAC address. And then it makes an entry, MAC IP association, in the ARP table. We got some time. I bet we can see this in live action. All right, I'm on Wi-Fi. I'm bringing up Wireshark. Do some fun stuff. Wireshark matters. Wireshark is used professionally. I've used Wireshark professionally for quite a few years to solve major networking and device problems by setting up networks to be able to analyze the data on them, very fine-grained, specific data, so you can see what's going in and out of like one device, like a voice over IP telephone, or a specialized network gateway, or a misbehaving general mismatch between data frame sizes, not data frames, between MTU sizes on a network and the MTU sizes expected by like a firewall, misconfigurations of things. Here we have Wireshark. It's a great tool for network protocol, network data analysis. It works on standard protocols, works on custom ones. It's extensible. The project, it's available from Wireshark.org. It's available for free, and it's one of the best tools you could use. It's built upon TCP dump, which is a command line utility for capturing data. All right, so we're going to capture from Wi-Fi. Press the shark thing. Now, right now, it is grabbing everything on my network, going in and out of this particular computer's Wi-Fi interface. Now, we were talking about ARP before, so we're going to do a protocol filter. So I typed into the filter box ARP and I hit enter. And now I only see the ARP. Now what we see with ARP is we see a broadcast. We can take a little detailed look at it. We'll pause the capture for now, or just stop it. We see address resolution protocol, the one that I selected. We see the sender IP address, and I recognize this as my gateway. It's MAC address. And then it's a broadcast, okay. That means that everything on the network is going to, see it, right? It's going to see that data. Now, specifically though, it's asking some information about this computer, 210. Who has 210? Tell the gateway. That's what this message means that I've highlighted here. What's going to happen is if 210 is on the network, it will reply back using the ARP reply message to tell the gateway, I'm 210, here's my MAC address. The MAC address is crucial because it's used at the data link layer, right? It's associated to the network interface card or the Wi-Fi card. And that's how the data is routed that last mile. Once you get onto the LAN, then you use the MAC address to deliver data to the devices on the network. So I don't see 210 right offhand, but here's 198. So 198 sent a message, and it gave the MAC address of 198. So you wonder, well, who's 198? It turns out 198 is my computer. I don't know which device 210 is, but definitely found 198. And if we dug through this data some more, we'd probably find some other systems replying back to the ARP broadcast. So when I send it back, how's it get sent? Let's see. There it is. So there's that message. And it comes from me, from 198, and it goes to the gateway. So that's what ARP looks like in Wireshark. Now, we're going to do some other things with Wireshark here. Got it up and running. We're going to do a ping command. I'm in a separate window typing in the command. I'm going to send 100 packets. I'm just pinging Google's DNS server 8.8.8.8. They have a good DNS server, so it's a good one to know and use. So we're going to start the capture again. Okay, I'm getting replies back from my pings. We see all that ARP traffic again. We'll turn off the filter. Now we're seeing everything. Now I'm seeing some new stuff in here. We're just going to stop right now. There's another protocol in here that's showing up, and it's going to 8.8.8. It's going to Google, it's a DNS server. And we see what it says here. It says it's a ping request. And the protocol is ICMP. That's a layer 3 protocol. So we can filter on that using Wireshark. There it is. We see all of these pings. I said I was sending 100. I've already stopped the capture, but it's still pinging away in my command window. Now if you take a look at the ping, what's it do? Well, how's it sending it, right? And what's it sending? It's sending some data. You can control the amount of data that it sends. Let's take a look at it. Look at that. It's sending the alphabet. Plus, well, it kind of wigs out. It gets up to W and then starts over again. I don't know what's wrong with X, Y, and Z. Those get excluded for some strange reason. And then what's the reply look like? So here's the reply from Google. And it sends back what I sent. What that enables you to do is make sure that your checksum is good. And there you go. You can see it right there. That's the checksum calculation, 05538. We see what we sent. Was that the right packet? Let's see if I can follow this. I can't follow. Now the checksum of what you response from frame 50. From frame 50. More like that's what I sent. Yeah. Anyway, the checksum is integral to network communications. It's the way TCP works, for example. You use checksums on the data that you send, and you verify the checksums when you receive it. And as long as the checksums match, you have received good data. If the checksums don't match, well, then you send out a request to retransmit the packet. So let's see if there's anything else interesting. So my ping is over, so my filter's not showing any traffic, so we'll clear the filter. And we see all this traffic coming through. What's this? I don't even know. The Quick Protocol, IETF. Payload, crypto, padding. Server hello, I picked up a handshake. So this looks like, I think this is related to HTTP. I think it's something new. Secret's not available. Yeah, I can't decrypt it. Encrypted traffic is not visible, or it's visible, but the decrypted contents are not visible in Wireshark unless you set it up specially, which I'm not going to go into, but you can set it up to actually handle decrypting data. So you can do some more, better analysis. There's interesting. That's a version 6 ping. There's a bunch of TCP data. These are IPv6 addresses. You can see acknowledgements, sequence numbers for reassembling the data that comes in. Got to assemble things in order, right? There's another ARP for 102. I wonder if 102 ever replied. Take a quick look in the filter. Looks like I cut it off too soon, so I never got a chance to see that reply. That's okay. I think by now you're probably getting the idea. There's a wealth of information in Wireshark. It takes some experience to understand it, to be able to read it, but at the end of the day, like here's a TCP packet I sent somewhere. At the end of the day, you can see all of the headers, all the information, everything going on. Source port, destination, port 443 tells me it's encrypted traffic. Flags and timestamps, all kinds of stuff going on. With regular, because I'm not so sure what this is. Looks like it goes to my gateway, which makes sense. If this was like an HTTP site, let's see if I can find one. I know there's some out there for testing. Okay. So this site I'm going to, it's specifically being slow right now. All right. I'm using a website that does not use SSL encryption to prove the point. Huh. It didn't let me through for some reason. Maybe the site's down. See if I can find some other sites. Find some other things that are not encrypted. I'm on a really slow site. I'm actually on the bulletin board system site that's been converted over for running on the internet. And some of these have a web-based simulator. And this one does. So we're going to start to capture again. And we should be able to see the traffic. Okay, we've got a bunch of traffic. So let's stop it and see if we're able to read the unencrypted HTTP traffic. Let's see if it shows up. So it's not that way. It's going to be TCP. And we want a port number. Let's see if I can get the port. Port 80. So unencrypted traffic. Let's see what happens. Nothing showed up. That's interesting. Let me see if I can find this another. Oh, the actual site was encrypted that the traffic was being routed through, so we're not going to find it this way. We can find it with 443 though. Yeah, we can't see the traffic exactly. We're going to try another way. Do one more quick test. What I'm doing is I'm about to try the Telnet protocol. Okay, so we're back in business. I've got a Telnet connection. And it's giving me a menu of options. I'm going to change this protocol to Telnet. Whoop, gotta spell that right. Now, will Telnet show up as a protocol? Maybe not. Might just have to try port 23. We'll look that up in a second. Okay, I'm typing some stuff in the options. Asking me my name. What type of graphics to use, and it sent me some funky graphics. Picture of it appears to be a game menu. Yeah. Play Trade Wars 2002. Okay. So let's see if we can find this traffic. I'm going to say play Trade Wars. I don't know anything about Trade Wars. Huh. I'm just sending traffic. For the purpose of sending traffic. Okay. So we've got a Telnet connection. I'm going to break out of the Telnet connection. Let's see, how do I quit? Okay. We quit, we lost the connection, we shut it down. So we're on port 2002 and it's Telnet. So we're going to try to figure out the IP address. So I'm going to ping the domain name, and now I have an IP address. IP.source. Okay. Oh, and we could do host as well. So we could just paste this in. No, it didn't like the host. Maybe I won't do that. Okay, 47. I thought it would resolve it for me, but it didn't like something. Green is good. And there's a bunch of traffic. Now, this traffic, there should be a lot of text that's readable because Telnet is an unencrypted protocol. These are its replies, and here's the data. Like I was just saying, how it's unencrypted, so we can actually read it. Copyright, Trade Wars game server, registered to abandon Stardock. So that's kind of cool. So you can see how Wireshark be useful for, sniffing out traffic. Here's the prompt that asks me, "What is your name?" So all the sources. So if I type in destination, actually, if I just do IPADDR, this should find any traffic to or from. So me going to open up the Telnet connection, all this traffic, right, is all part of the communications between me and that one server. And since it's Telnet, as I said, nothing's encrypted. So Telnet's, other protocols that are not encrypted, you can read the information. Or you have to set up Wireshark with the correct certificates in order to be able to decrypt the information. But for learning how things work, if you open up a Telnet session or you do some FTP, it just makes it a little friendlier to be able to read the data. And you can do some other tricks here, like I can follow this stream And there you go. This is practically what the screen of this probably is not getting picked up in my my window. Let's see if I can change the window quickly. That's not the window. Yeah, that's the window. So this is the result of following a TCP stream in Telnet. It shows me all the stuff that was going back and forth. So again, it's a very useful tool. It kind of stitches together the frames the same way a browser does. Like here's a bunch of data. So I said use ANSI graphics, or it asked me that, and I said yes. And then it sent me a picture. Remember I said it's sending me a picture. Well, this is the data of the picture that it was sending. And then, you know, a few other things about this particular game. Okay. I'll go back to, oh, it went back automatically. That's nice. All right, so we're back in our Wireshark window. So analyzing data on your network. Wireshark's great for it. You could set up a little network with send unencrypted stuff around so that you can easily analyze it, or send encrypted stuff around and learn how to configure Wireshark to decrypt things. All right. So, like I said, I highly recommend getting Wireshark. If you're going to be working in IT, you're going to need to know how these things work. Oh wow, and they've added some new menus here. Telephony. That's great. Real-time streaming protocol analysis. So, you know, phone call stuff. Some of those are pretty old. Might not have much use for GSM. SIP though, SIP, flow statistics, that's good stuff. Bluetooth, you can capture USB traffic if you put on the right additional tools. There's a scripting console. Yeah, so you can see it's a rich, complicated application's been going on under development for maybe as long as 20 years. Let me see if I can find any original information on it. It had a different name when it started. It was called Ethereal back in the 2000s. Yeah. What kind of license? GNU General Public License version 2. So it's a open source project. All right, well that's enough on Wireshark. I hope this makes you interested in trying it out at least. Like I said, professionally, it's been a very useful tool for me for solving complicated network and device hardware problems. ICMP. That's a fancy name for ping. Ping is a layer 3 protocol. IGMP and OSPF. These have to do with routing. Routers have their own special protocols. Open shortest path first. It's a protocol in a router tries to figure out, you know, what's the shortest meaning time-wise, right? It's sending traffic through. It's got places it can send the traffic. What is the next place on the right path to where it's trying to get to that will result in the fastest delivery of data? So it's not necessarily about distance, okay, but it could be. This is IGMP, I believe it's a yeah. It is a multicast protocol for routers. Again, we can talk to each other using some broadcast type of data. Let's see here. Manage multicast group membership between hosts and routers. Streaming, gaming, where there's multicast. So like right now, is this a multicast event? It might be. I don't know. I don't know how GoToMeeting's architecture works. I suspect it's not multicast, but if we were doing it like on our own network, it might, like inside a network, if I was having a teleconference or something, it might broadcast to everybody, as opposed to sending separate traffic streams to everybody. Because I'm sending 10 people's traffic, I'm sending it to 10 different people. That's not efficient. I'd rather send it once than like broadcast and then have it sent. With something like GoToMeeting, it's probably being distributed through like a fan out algorithm where I send it once to Amazon, where the GoToMeeting server is, and then for the people connected, it has to send it a separate connection to each of those people. I can't broadcast it over the internet. Let's put it that way. So broadcasting would be for internal. If it's broadcast over the internet, then where would it be going, right? You can't just go to the whole internet. It doesn't make any sense. All right, moving up the stack. Transport layer. Oh, let's see, I have a question. Here. Which layer is responsible for routing packets across networks? That would be the network layer. We just talked about that. Okay. Now, last week in class, we talked a little bit about dumb hubs and switches. And I said earlier in this talk that a switch has some intelligence in it where it's able to, well, I guess the switch will use ARP, and it will send out the commands to find out what's connected. Actually, I'm not sure I know how it finds out who, how it initially gets connected. Let's find out. This will be enlightening. Okay. It doesn't send ARP commands, but it's conceptually the same. It has a table for storing the relationships between MAC address, IP address, and the port and the switch. So your computer gets plugged in and it's sending data. It's always sending data. And the switch just looks at the data and goes, oh, there's the MAC address. You can see the MAC address in the frames. We were just looking at some in Wireshark a minute ago. So it saves that. So there you go. Now your switch is initialized. A hub sends all the data to anything connected. It's stupid. The switch, once it learns the MAC address for a given port, sends each device's address only out that one port. The hub will send it out every port. What's that mean? It means you can go into something known as promiscuous mode and run Wireshark, for example, in promiscuous mode. Let's see. Go to capture options. Just show you. This is cool. Back to Wireshark for a minute. So we'll go to capture options. I hope this window shows. It might not show because it's, I got to share this individual window that it popped up, otherwise it won't work. You won't be able to see it. That's not it. I don't think it's going to show you. Sorry. No, can't do that. Well, in the capture options window, there's a checkbox for enable promiscuous mode on all interfaces. So that tells the network card, just look at all the data, every bit of data on the network. And that lets you analyze the whole network. Now, if you have a dumb hub, then you can see all the data. If you don't have a dumb hub, then you're not going to be able to see this stuff, and you're going to need something like a port replicator on the switch, which is what I'd also mentioned before. Okay, so back to this. This transport layer. Here we find the transport control protocol. This is the important one, TCP, as in TCP/IP, transport control protocol for the Internet protocol. UDP, user datagram protocol. The difference between the two, transport is reliable, means any data you send will reliably get there. The server and the client will talk to each other as necessary to make sure that if there's any mistakes in the data, there will be a retransmission. And you'll get the right data. Since everything is numbered, right, sequence numbers on the packets, you can reassemble it in proper order, the proper data, so it's reliable. UDP is unreliable. It is simply sent and forgotten about. If it gets there, great. Works good for video, works good for audio. It's more efficient than TCP because you don't have any retransmissions, and there's a little less overhead in the individual packets if you look at them with Wireshark. SSL, this is security, right? So when you see the little lock in your browser window, this will tell you information about the security. This site has a valid certificate, look at that, issued by a trusted authority. Cool, that's good to know. Ooh, clicking that icon there, I get, well, I'm not so sure this is showing up. Might have to, but if you, actually, I bet none of these little pop-ups showed up. That's kind of horrible. Well, you can get the certificate information. I'm actually on a Pinterest website. That's where this diagram is from. And you can see who issued it, how long it's good for, when's it expire. This one's really short-lived, less than a year. So every year these guys need new certificates. So every now and then you hit websites where they've lost their certificate, things are broken and they don't connect right, or it's untrusted because it's expired. So end-to-end connection and reliability. That describes TCP very well. It doesn't describe UDP at all because UDP doesn't have reliability or end-to-end connections. I don't know what these other two are, so I'm not going to talk about them. We're going to keep moving up the stack. Inter-host communication. Ooh, that's a big term. Clients and servers, right? That was the topic, well, in the lecture, and also all of last week's discussion in office hours was on history of client-server computing. So all of these protocols, these are good protocols here. TCP, as we mentioned before, SIP, Session Initiation Protocol, RTP, Real-Time Protocol. Real-Time Protocol is for real-time media, audio and video in real time. You know, not like a file you download that happens to be music or a movie, but something happening in real time. SIP is used in conjunction with voice over IP for all of the, well, pretty much all the telephones these days. I believe we're using SIP and VoIP clients for our phone communications as well, especially when you're using an application like WhatsApp. Probably some other communications messenger, Facebook Messenger. So when you make a phone call using Messenger or you make a phone call using WhatsApp, it's being operated as a voice over IP client, and it uses SIP, the Session Initiation Protocol, to establish communications, to have a handshake between your phone and the phone you're calling, and some stuff in between before a connection might be set up directly between your phone and the other person's phone. If you're able to set that up directly, might have to go through some relays. RPC named pipes, so remote procedure calls. So if you're on the same network with computers, they can talk to each other and do remote procedure calls. Actually, there's technologies for doing remote procedure calls, I think, over the internet at large. I don't think I'd want to do that though, for security reasons. Performance, okay, yeah, a few things. Might not work over the internet. And the answer is does not work over the internet. Well, it's a Windows mechanism. Okay. Processes on the same machine or between machines on the same LAN. Okay. Uses SMB. That's interesting. Server message block. SMB is the same protocol that allows file sharing. You can file share using it from a Windows computer to another Windows computer, or Windows to an iPad, or a MacBook. Yeah, don't want to use SMB over the internet. There have been some historically bad exploits, stole a lot of data because people tried to do that. Yeah, so overnamed pipes is a LAN technology, but there are ways apparently to do internet RPC. I'm not going to go into that. That's some advanced networking programming. So setting up sessions. This also means setting up sockets. I know I mentioned the word socket before. Socket is an IP address and a port combination, and the type of protocol. So I can make a TCP socket and a UDP socket. They could actually be the same IP address and the same port, but because they're different protocols, the computer sees them differently. So there's no conflict there. You need the socket set up in order to have the communications. They have the literal read and write, wait, open, close, all of those semantics for setting up communications over the network. All right, let's see if I'm sharing the right thing. I'm not sharing the right thing. Good thing I checked. Back to this. So I don't know when I switched out of it. Oh no, it was during this talk when I was trying to look up something about promiscuous. Oh, that might have been a while back. Well, anyway, transport layer, here it is. This is the heart of the networking stuff between security and reliable transmission of data. Then on a LAN, you can use RPC named pipes, or within a device, within a computer, you can use inter-process communications. You can have these inside a computer so that different processes, literally different processes, different applications within a computer can talk to each other. Type of, you can think of it like distributed computing, but all done within the computer itself. And then the main protocols there are setting up your sockets for TCP, for SIP, for RTP, to set up good old client-server communications, right? Where you have to set up a connection on a socket, which is a port and an IP address and a protocol. You connect to the other guy. He you wait for him to connect and accept your connection request. If he doesn't, that's a timeout. Timeouts are typically like 20 seconds. Okay? If he accepts the connection, right, then you wake back up, you get notified that he's accepted the connection. Now you can open it and write data, read data to and from the sockets that you've established. And there's some complex interplay and threads that go on, and making sure that you are reading and writing properly, reading and writing efficiently as you send data around. And also, as programming has progressed, we've got very advanced machines now, very advanced threading, networking communications, and good programming tools and practices and knowledge to support it. The early days, 10 years ago, 15 years ago, you could write apps on an Android device that didn't behave well, that would use network communication on the main thread. And if that blocked while you're waiting to connect to something or waiting to get data from something, then the rest of the application wouldn't work because you were on the main thread. And if you're blocking the main thread, then nothing else is going to work because the main thread would have like your user interface on it. So you're basically blocking the app itself while waiting for communications. Now, because of problems, people programming things wrong, not recognizing they needed separate threads for the UI and separate threads for networking. It's actually built into like the development kit, where you're prevented from building an app wrong. That's a good thing. So networking is on a thread other than the user interface thread. So like you can do stuff in your web browser, open up different tabs, interact with a web page while it's sending and receiving data. And from looking at Wireshark, it's always sending and receiving data. If we didn't have multi-threaded networking going on, then you wouldn't be able to do that. And you wouldn't be able to do anything with your app. It would just be like sitting there waiting for data. But it doesn't work that way now. It works much better. Okay, presentation. Or actually, here it says the presentation layer, the description says data representation and encryption. I throw in encoding and decoding, not just encrypting and decrypting. There's more to it. And you can see that explicitly here because it says JPEG. JPEG's not about encryption, it's about encoding and decoding. Any of the images, doc files, encoding and decoding. MP3, encoding and decoding the data. AVI, which is a video format, encode and decode. So, very important layer though, nonetheless. Just want you to understand it's not just about encrypting and decrypting data. It's about encoding and decoding the components in a web page, for example. And why are they at this level? Well, because at the top level is where your applications are that use all that data. You can't read the encrypted stuff, right? So it gets decrypted before it bubbles up to the application layer. If you just had a bunch of raw data for a JPEG image or a PNG or whatever, it wouldn't do you any good seeing that at the application layer because it's just a bunch of data. Instead, the presentation layer recognizes the data through headers and such, turns it into something, right? A picture that your browser can understand, or video or audio that your browser can understand. And then it is able to properly display it and show it to you, or play the music or play the video. That's what's going on at this top layer. So you see www/http. So the World Wide Web uses the Hypertext Transfer Protocol. That's what that's saying. That's your web browser. Peer-to-peer. So people are still using some peer-to-peer for more efficient file transfers. I don't know who it's more efficient for. It's not necessarily more efficient for you. It's more efficient for the person you're receiving a file from, because you may receive it from 10 different people. So there's less network traffic on that one source that's sending it. It's spread around. See, the email protocols up here. That's what POP and SMTP are. Telnet, we showed you Telnet last week in class. It was one of the earliest protocols. FTP was even a little older than Telnet, because the first thing people needed to do is send files around. Then they wanted to interact with remote servers, so they started using Telnet. At some point, email came along. I know it was around in the 80s. We're sending messages. Don't think it was these protocols necessarily. Probably sending messages even before that. What else? DNS, the domain name service. Because we don't memorize IP addresses, you may know a couple. Sure. You should know Google's DNS 8.8.8.8. It's a good, reliable DNS service to use. That's the service that tells you the IP address of a web page. Now, most of the common ones, you go to the same websites a lot, and your browser will cache them. Actually, the operating system will cache the IP address for that. So it doesn't have to go to a DNS server all the time. You already know the IP address. That makes the network more efficient. Now, DNS is global, highly protected, because it's critical infrastructure. What is it, Route 53? So that's what Amazon calls their DNS service. It's on port 53. So the first 1,024 ports are reserved, and many of them are specifically reserved for very specific internet services. These are some things you need to know for various examinations and certifications. HTTP port 80, HTTPS port 443, Telnet is at port 25, FTP 21. The reason is firewalls use port numbers. So if you're configuring a firewall, you might want to know what you're doing. Make sure you're configuring it right. Blocking the right traffic or letting the correct traffic through. Firewalls, important stuff. So let's ask a few more quiz questions. Which protocol is commonly used at the transport layer for reliable communication? Is it ARP, TCP, IP, or UDP? Well, IP is at the network layer, one below transport. ARP is way down there. It deals with MAC addresses and IP addresses. So that means that ARP must be must be at layer 3, right? Because at layer 3, you have an IP address and a MAC address from layer 2. So it'd be a layer 3 protocol. IP is layer 3, because that's where you get your addresses. UDP is not reliable. TCP, though, is reliable. And the T stands for transport. So TCP is at the transport layer and used for reliable communications. What is the main function of the presentation layer? Well, this is kind of like a review. We just talked about it. Encoding and decoding images, audio, video. Encrypting and decrypting secure communications. Making sure that the data, the raw data, is recognized and then converted to a format that you can see in your web browser. Or that other apps may just need, right? You got to decrypt everything, so that you can receive it in an email or something like that. Which layer does the HTTP protocol operate on? Well, that is in your web browser, which is an application which operates at application layer, which is layer 7. We talked about the difference between a hub and a switch. Hub sends traffic everywhere. A switch has some intelligence and it only sends your traffic out the port associated to your MAC address for your IP. Match the OSI layer to its primary function. Ooh, that's a good one. Physical. It's not the user interface. It's not reliable data transfer. It can be anything. It can be reliable or unreliable. Raw bits. There's no protocol information at the physical layer. If you think about it, it's just transmitting electrical pulses on a wire, representing binary data, individual bits. You have no idea what it is. You need something to interpret it, to turn it into protocols, to recognize it, to synchronize to it, so that you know how much do you read at a time and decide, okay, that's a chunk of data I can read and understand. And then you can dissect it in Wireshark. And then you take the next chunk and dissect it in Wireshark, right? Or process it up the stack with whatever other application you're using. Wireshark's just convenient because it shows you all of the data. It shows you what these packets and frames and whatnot look like. But you need some intelligence, some abstraction on the raw bits in order to make sense of it. A transport layer, transport control protocol, it's reliable. So we know it's reliable data transfer. That's what transport layer is doing, typically. It does unreliable also, but in this case there was it's like a question where it lists some options. The correct option is reliable data transfer. And then application level. So at the application level, top of the stack, all the data has been received, all the data has been decoded or decrypted, and now it's viewable to us. It could be a Word document, could be images, music, whatever. It's viewable to us in the user interface of the web browser. So that's what is going on with the app.